And I'm going to kind of move on to enhanced oil recovery. We have typically had a whole class on enhanced oil recovery, and it's an elective class. Dr. Lake often teaches it, so you may want to take it next year. But I wanted to give an overview of it because it's a follow-up to what we're doing, secondary recovery, and they're very much related. I'd like to show you a plot that you've seen before. You almost definitely saw it in Reservoir 1, and I think I showed it on the very first day of class this semester. These are qualitative schematics. They're not perfect by any means, but what you learned in Reservoir 1 is that as you started producing, the average reservoir pressure, this sort of blue line, and the well pressure, this yellowish green line, both decrease. Okay? But they decrease at the same rate, and you might be able to operate your well at constant rate. I don't know, maybe 1,000 barrels per day. During that time, the oil saturation doesn't change much. And that seems weird because we won't be producing much water, but we are producing oil. So how does the oil saturation not decrease? Well, the reason is because the oil expands to fill the empty volume. So the oil saturation is relatively constant. Once the producer well reaches some limiting pressure, on project number 1, that was 2,100 psi. Remember, you put that constraint on there because we didn't want to drop below the bubble point. After that, we fix that constraint. The reservoir pressure continues to decrease. The drawdown pressure, the pressure between the reservoir and producer, decreases, and because of that, the oil rate declines with time. And you might remember from Reservoir 1, you did some decline curve analysis. Many reservoir engineers do that as a big part of their job. That was Reservoir 1. Oftentimes we do some sort of secondary recovery technique. This is usually in conventional reservoirs. It's harder to do in unconventionals. I might try to talk about that in a few minutes. There's more than one secondary method, but the most common is water flooding, and that's what we've talked about. So when you water flood, you have another well, an injector well, of course, where you inject water, and it pushes the oil towards the producer. When it does that, the pressure increases of the reservoir, and you get this nice displacement, and the oil rate increases. But then what happens is the water you're injected starts reaching the producer well, and you start producing water. So the dashed line is a total rate, but that includes a lot of water, and the oil rate is what we really care about, is the black line, and it declines, and eventually gets to a point where it's no longer economic. So EL stands for economic limit. You can see that in this case, both the reservoir pressure and the well injector pressure may increase with time, and we might keep our bottom hole pressure of the producer well constant. In this case, the oil saturation does decrease. It does decrease. Okay, that's because the oil is being replaced by water. In primary recovery, compressibility, including expansion of the oil, is a primary mechanism. In secondary recovery, it's not compressibility. In fact, we usually neglect compressibility, as we've done in this class and in secondary recovery, and the primary mechanism is pressure maintenance and the displacement of oil by water. This is kind of where we finished off in class, and maybe for a typical sandstone or carbonate reservoir, you might produce 10% of the oil from primary recovery, another 25% from secondary recovery. That's a little more than a third. That's just an average, right? Every reservoir varies. That means that we're leaving 2/3 of the oil behind. And that's a lot, right? And that's a lot. And most of the time, we don't do anything about it. We just move on and go to the next reservoir. Okay, but one of the reasons I like being a reservoir engineer, one of the reasons I find it exciting, is because there's so much potential there. So we got 2/3 of the reservoir that's still got the oil in there. If we can be really creative and really good engineers, we can get a sizable portion of that out. And a big portion of my research is on tertiary, also called enhanced oil recovery. And in that, we inject other fluids like polymers, surfactants, carbon dioxide, or steam to improve recovery. And you get another bump and then it goes down. The oil saturation decreases with time. So this is a figure that Dr. Larry Lake put together, and I've used it in every single reservoir engineering class I've taught because I really like it. And just a few more comments about primary and secondary recovery. If you have a conventional well, a conventional reservoir, okay, that's a sandstone or carbonate, usually on the order of 1 to 1,000 millidarcies. Okay, the oil recovery is going to be 10 to 20%. Okay, something like that from primary recovery. You use techniques like artificial lift and whatnot to improve that. In unconventional reservoirs and shales, okay, we're often talking on the order of less than 1,000 nanodarcies. So maybe 1,000,000 times less than that, okay? That is a really small permeability. For decades we knew about them, but we didn't even bother because it was impossible to create. And of course we've developed horizontal wells, hydraulic fracturing, and that has led to 5+% primary recovery. And yes, you're reading that right. This is that in a typical unconventional reservoir like the Bakken or the Permian Basin or something, we might produce on the order of 5% from primary recovery, and then we're often done. We don't even bother with secondary or tertiary recovery. So you can imagine that there's an enormous amount of potential there in unconventionals. And despite this low recovery, they're still very economical, and of course that's a big portion of our production. Secondary recovery, and different people have defined this. The way that Dr. Lake defines it is the injection of any fluid after primary recovery that already exists in the reservoir. So the most common being water flood. Okay, you can inject like natural gas too. That's another common one, but water flooding is the most common. And in conventional reservoirs, we might get an additional 10 to 30%, and this might take decades. All right, so primary recovery might occur over several months or just a couple of years. You might water flood for decades. We're still water flooding reservoirs that we found decades ago. Unconventional, I'm going to put NA, okay? And that's one of the reasons why we didn't talk very much about unconventionals in this class, is because water flooding shale reservoirs is not all that practical. The pores are so small in shale reservoirs that it's difficult to inject that water. The amount of pressure you would need to flow through there is extremely high. So we don't usually water flood, but we're starting to do that a little bit, and this might be an area of the future. Remember, primary recovery in unconventionals wasn't even a thing 20 or so years ago. Water flooding may be standard, or other secondary techniques might be standard in a few decades, and you might be the person that helps to develop that technology. And I say that it's NA, I'm referring specifically to water flooding, because there are other techniques like injecting natural gas and other techniques that are usually tertiary or enhanced oil recovery techniques. Okay, let me talk a little bit about that. Remember that the dimensionless oil recovery is the displacement efficiency times the aerial sweep efficiency times the vertical sweep efficiency times the initial oil recovery minus SOR. So those three different sweep efficiencies, I'll just call them E, are functions of time and the mobility ratio. All right. So time or dimensionless time, pore volumes injected. And remember what I've always said is that if we were willing to wait long enough, then this would go to, then E would go to 1, okay, regardless of the mobility ratio. But we're not, because that might take hundreds of thousands or millions of years to do that. So it's very much a function of mobility ratio. And I'll talk about that in just a moment. Well, let me just define. So remember that M is the mobility ratio. And it is equal to KRW mu O over KRO mu W. The other thing we might want to try to improve is SOR, which is a function of the capillary number. What is the capillary number? A capillary number is a dimensionless number, which is the water or aqueous phase viscosity times the velocity divided by the surface tension, or the interfacial tension. So, in enhanced oil recovery, our goal is to improve the mobility ratio to make it smaller, right? So we want the mobility ratio to be smaller. That means either increasing the aqueous phase viscosity, decreasing the oleic phase viscosity, or decreasing the interfacial tension. Now, it's harder to change the relative permeabilities. You can see that we got the aqueous phase viscosity and velocity on the numerator. Those are both difficult to have a large effect on, and I'll explain why. So, if you were to plot SOR, the residual oil saturation, versus the capillary number, remember that's viscosity times velocity divided by interfacial tension, you get what's called a capillary desaturation curve. You can create this in the lab. It looks something like this. This is a linear scale, so maybe this is like 0.3 or something. It all depends on the rock and the oil. This is a linear scale. This is a logarithmic scale. So this might be 10 to the minus 9, 10 to the minus 8, 10 to the minus 7, 10 to the minus 6, 10 to the minus 5, 10 to the minus 4. Okay? So this is logarithmic. A typical water flood might be somewhere over here. So you can say, well, I can decrease SOR by increasing the capillary number, and I can increase the viscosity. And I know that, I've been telling you all semester that we could do that by using polymers or something. So we could increase the viscosity, or we could increase the velocity. That would increase the capillary number. Fortunately, that doesn't work very well. And the reason why is because we're here on this flat part of the curve, and this is a logarithmic scale. You would have to increase the viscosity or the velocity by several orders of magnitude in order to make a real difference. And that's just not really practical. So what that means is that we don't use polymers and other viscosifying agents to decrease SOR, but we can change the interfacial tension, and that's what surfactants are used for. Okay, so summary, EOR methods are lumped into decreasing the mobility ratio M. The way we do that is to increase the water viscosity. Those are polymer type methods, which are chemical EOR methods, or decrease the oil viscosity, right? So we can decrease the oil viscosity. Those are thermal or gas injection. Okay, so what does thermal methods do? It means heating it up, right? It works just like you put your cooking oil on the stove in the morning, right? It's super thick and viscous. You put it on the stove, you heat it up, and then it flows really easily, right? It's exactly the same thing. We're going to heat this up, usually with steam. There's other ways to do it, like electromagnetic heaters and other things. But you heat up the oil, it decreases the oil viscosity, and then you have a lower mobility ratio. And you think about a reservoir, say in Canada, that's got really, really, really high viscosities. Like, I'm not talking, of, 10 times as much as water. I'm talking thousands or million times the viscosity of water. It's almost like a solid. Then that has a big impact. Gas injecting, you can inject things like carbon dioxide or methane, maybe nitrogen, in order to decrease the viscosity. And then the other is, of course, to increase the capillary number. And that is to decrease the interfacial tension sigma. You learned about that in petrophysics. Okay, so oil and water don't mix. They've got some sort of interfacial tension. What surfactants are, this is a different chemical EOR method. Is there just soaps? They're soaps or detergents. Okay. And they work the same way. So just like you use detergent to clean your dishes or clean your clothes or use soap to clean your hand, if you've got some sort of grease, some sort of oil or non-wetting fluid, and you try to use water to clean it up, it doesn't clean up so well. But if you add a soap or detergent, it reduces the interfacial tension and it comes off really easy. It's the same idea in a reservoir. The oil and water don't mix and they're separated and you get trapped oil. But if you reduce the interfacial tension with a surfactant, then it flows much easier. So the main types of EOR methods are chemical. And I like talking about this because this is my area of research. And it's to use polymers and or surfactants. Okay. And remember they do two very different things. The polymers decrease the mobility ratio. The surfactants increase the capillary number. Okay, and that decreases the SOR. So they work in two different ways. Many times they're used in conjunction with each other. You'll inject a surfactant and then you'll use a polymer drive for mobility control. We call that an SP flood, surfactant polymer flood. The next is thermal, as I mentioned, which is steam or electromagnetic heating. And the last one is gas injection. It's usually CO2, but it could be methane and nitrogen. Okay. There are other kind of smaller, less used techniques. One of them is microbial EOR. So what they do is they inject microbes and they feed off the nutrients in the reservoir, and at the oil-water interface they reduce the interfacial tension. So in a way they work like surfactants. Okay, so let me talk about polymers. I like talking about that because that's what I do a lot of my research in. What polymers are is they're long chain, usually organic molecules. They're usually, for our purposes anyway, dissolved in water. You all are familiar with polymers. Okay, you've heard of polyethylene, polypropylene. Most plastics are polymers, right? So you've heard of those. These are water dissolvable polymers that increase the viscosity. And so remember I said that these are long chains, so what you might have is carbon molecules. This would be, these are connected to hydrogens, right? And I stopped at a point, but these are huge. These molecules are gigantic. They have a molecular weight of millions of grams per mole or pounds per pound mole, which means that there's thousands or more carbon atoms in there. One common polymer used in EOR is called hydroxy polyacrylamide. Okay, or we'll call it HPAM for short. Let me see if I can. So here's the structure of hydrolyzed polyacrylamide. So you could see what that looks like, and it's this molecule then connected to this molecule, and it's got, it was sort of like the polyethylene I showed, but then it's got this C double bond O and in this NH2 group on there, and I've got this Y and X minus Y, so Y could be huge, right? It could be thousands, and X could be that. This is hydroxy polyacrylamide. That's what the chemical formula looks like. Another less commonly used one, they used to use this one years ago, decades ago. They don't use it so much anymore. It's called xanthan gum. And I wanted to show that one because even though we don't use it as much in EOR, if you check the ingredients on most of your food, especially the processed food, there'll be xanthan gum in there. So you've got a chemical EOR agent in a lot of your food. These polymers have a high viscosity. Okay, and what I mean by that is it's going to be greater than 1 centipoise to maybe 1,000 or so centipoise. Okay. So water has a viscosity of 1 centipoise. At reservoir conditions where the temperature is high, maybe it's half of that, half a centipoise. Polymer, the only reason it's useful is because it's higher. It gives us a better mobility ratio. This viscosity of the polymer is a function of the molecular weight, the concentration, the salinity, that's the salt content, as well as things like temperature, etc. Okay. And the type. So, by the way, I mentioned HPAM. There are some derivatives of HPAM that have been developed that are more suited for particular reservoirs. Okay, so you can increase the molecular weight. That's to make this molecule bigger. You can increase the concentration. Right? We only add a very small weight percent in there, but if you add more, then it's going to make it even thicker. Probably not a surprise. It's a function of salinity, and actually the lower the salt content, the higher the viscosity. It's a function of temperature. You can imagine it decreases with increasing temperature, just like most fluids. Some of the issues are they do degrade at high salinity, temperature, or maybe velocity. Okay, by degrade I mean it breaks up the molecule and then it decreases the viscosity. Okay, so it sort of defeats its point, right? So it's very hard to get a good viscosity of these things, and the way you compensate for that is that you increase the concentration. If you increase the concentration, then that costs more money, and so the issue is cost, right? Water's cheap. Okay, when you start adding any of these enhanced oil recovery methods are expensive, so that's why we often don't do them. It's just not economically beneficial. So we're always looking for ways to improve the cost. The other is the injectivity. Okay. So the whole point is that these polymers have a high viscosity, which improves the mobility ratio. But it's harder to inject a high viscosity fluid than a low viscosity fluid. That just makes common sense, right? It's harder to inject. For the same pressure drop, you're going to get less flow rate, or for the same flow rate, you'll get a lot bigger pressure drop. And in fact, you remember from Reservoir 1 that we learned that the production or injection rate in this case is equal to the productivity index times the bottom hole pressure minus the reservoir pressure. So for given average pressure and bottom hole pressure, it's a function of J, and J is inversely proportional to the aqueous phase viscosity. So if you increase the viscosity by a factor of 10 or 100, then that means that your injection rate is going to decrease by 10 or 100 for the same bottom hole pressure. Or alternatively, if you wanted to keep the rate up, then the bottom hole pressure would have to be higher. And if you injected too high of a bottom hole pressure, then you might fracture the rock, and you don't want that. Okay, so that's a problem. The nice property of polymers is that it partially, not entirely, but it partially offsets that. So if you were to plot the viscosity versus the shear rate, okay, and shear rate is proportional to velocity divided by the square root of permeability. It's more complicated than that, but it's proportional to that, so that's good enough for us. You might remember from your transport phenomena class that for a Newtonian fluid like water, the viscosity is constant. But you might also remember that certain non-Newtonian fluids, like polymers, are shear thinning, meaning that they decrease in viscosity with shear rate. Now, most polymers aren't completely shear thinning. At very low shear rates, they might be constant, then they might shear thin, and then they might be constant again at higher. And so this is a log scale, so I'm going to put log of viscosity versus log of shear rate. This might be 100 centipoise, this might be 1 centipoise. So depending on your velocity, it can change by a couple orders of magnitude. Why is that a good thing? Well, it's a good thing because near your injection well, your velocities are very high, right? Remember that analogy I've given throughout the semester that if you look at a bathtub or a sink and you look right by the drain, the fluid is flowing really fast. And if you go far away in the bathtub, it's flowing really slowly. Same idea for the wells is that the velocities are very high near the well. So near the well where you're trying to inject, the viscosity is relatively low. And then far away from the well where the velocities are lower, you have a high viscosity, and that's good for mobility control. So the shear thinning behavior of these non-Newtonian polymers is beneficial to enhanced oil recovery. Now, it just partially offsets that. Okay, I put 1 centipoise here. It's usually hard to get that low. That would be like water. So we're always looking for polymers that have ideal rheological properties. So let me briefly talk about surfactants. As I mentioned, these are soaps or detergents. Okay. Now we don't just use any surfactant. We can't just take the soap we have in the kitchen and go inject it into the reservoir. We develop very special surfactants for a specific oil and a specific reservoir. And that takes a lot of work. And as I mentioned, it reduces the IFT. Okay. You could reduce it all the way to 0, then it's just going to be miscible with water and then just flow through it, and that would be perfect. Oftentimes with surfactants, we can get to really, really low interfacial tensions. And what happens is that the oil starts becoming miscible in the water. It's not completely miscible, but you start to create what we call emulsions. So oil in water, or water in oil, or sometimes something between, what we call a microemulsion. These can be expensive. All right. It's not cheap, soap in the kitchen's cheap, but when you're injecting this much, it can be expensive. And one of the things that we try to minimize is the amount of what's called surfactant retention. It's the amount of surfactant that gets left behind in the reservoir, and we want to minimize that, and we can reuse it and whatnot. So surfactants can be expensive. Remember, they are used to reduce SOR, and for that reason, they're often used with polymer. So SOR reduces, so surfactant reduces the SOR, polymer improves the mobility ratio, and we can have what's called an SP flood. So you inject surfactant followed by polymer. So in gas EOR, we inject CO2 is the most common, or other gases. CH4, nitrogen, etc. Has a couple of mechanisms. One is to reduces the oil viscosity. Okay, that's probably not a surprise, right? So if you have this gas and you mix it somehow, and you do have these miscible versus immiscible displacements, but if there is some mixing with low viscosity carbon dioxide gas, then it's going to reduce its viscosity. So it does reduce its viscosity, and it also can swell the oil, which makes it a little bit easier to flow and produce, and it might increase the pressure. This is perhaps the most popular in the US. It's been used for very many decades. One of the issues is availability of the gas, especially if it's CO2. All right. So you might not have CO2 available to you, and that's one issue. And that's one of the reasons why sometimes methane is used. So maybe you produce oil, you get some solution gas that's created, you maybe do some separations, and then you inject, or not, but you inject your produced gas. And that's sometimes not as good as CO2, but it might be what you have available. I'd like to say a couple things about gas EOR. The first is that it is a technique that is gaining a lot of attention for unconventional shale reservoirs. So as I mentioned, it's really hard to inject water, high viscosity, bigger molecules into these nanopore size shale reservoirs. CO2 is a little bit more feasible because it's lower viscosity and smaller molecule. And so it's been used. I actually wrote a few publications about it quite some time ago, and it's really, this technique has really received a lot of attention recently. Now, it works a little bit differently than what we do in a typical water flood. It's very, very difficult in a shale reservoir to inject from an injector well and produce from a producer well that might be hundreds or thousands of feet away. Remember that these shales are like really, really small permeability, and it's very, very difficult to flow. If you looked at shale, you would never guess that it had some sort of porosity or permeability. They look like solids. So it's very difficult to inject from an injector and produce from a producer far away. Instead, what we do is a technique which we call huff and puff. Yeah, just like the little pigs, right? So you huff and puff. So the idea is that you use the same well as an injector and producer. You inject the CO2, goes into the reservoir, mixes with the oil, it swells, the pressure increases. Then after you shut in that well, that's when it does all the mixing. Then after some time, you open up the well, and then you produce the oil along with the CO2, and then you inject CO2 again, and then you produce it. So it's a huff and puff process. That's one way to do that. And at least in the paper we wrote, we found that if you re-inject produced gas, that can be almost as effective as doing carbon dioxide. There's another thing I want to say about CO2 for gas EOR, and that is that we've been doing this for decades. We've been injecting CO2 underground for decades for the purpose of enhanced oil recovery. As most of you know, carbon management has become a big issue, and I imagine will be a big part of many of your careers, is that finding something to do with CO2 as opposed to putting it into the atmosphere. One solution, our solution, is carbon capture, utilization, and storage, CCUS, which most of you know refers to capturing CO2 from things like power plants, re-injecting it underground, either for storage, that's the S, and you just get it there and trap there for no other reason to trap it, or utilization, which means using the CO2 for something. Our expertise in gas EOR has made this possible. And so I believe that if there's a solution to CO2, it is CCUS is a big part of that solution. And our knowledge gained from this is contributing to this. And whether or not we just store it in, say, an aquifer and just leave it there, or my favorite is utilization. So utilization is basically gas EOR. And I'm really excited about that. I do a lot of research in CCUS. And I'm excited about the utilization aspect because I consider it the world's greatest recycling system. We produce oil, we burn it, we create CO2. Instead of putting it in the atmosphere, we re-inject it back underground. We create more oil, which creates more CO2, and we put it back underground. Okay, it's a little bit more complicated than that, but that's the general idea. And so I consider that the world's greatest recycling system. And I think that could be a future of what we do as petroleum engineers. I'm running out of time, so I'll just briefly mention thermal methods. Okay, and as I said, you can do steam or electromagnetic heating. You can put actual heaters down in the reservoir. And again, the idea, the way that this works is that you heat up the oil and the viscosity decreases, can be by orders of magnitude, right? And if you're talking about oils in Canada, they might be millions of centipoise, and you can decrease this by orders of magnitude, and that is really effective method. So anyway, you could heat it, steam, electromagnetic heating. They have a process called SAGD, steam assisted gravity drainage. The way that works is that you have two parallel horizontal wells, and you inject steam, and then the steam results in a lower viscosity oil, which then can drain down to the other producer well. So that mostly completes my very, very brief overview of enhanced oil recovery.